is like the model give you findings that aren't actually in the image. The second is sycophancy. The model abandoned its correct answer just to agree with the user. You tell the model it is wrong and it will hold its correct answer. Now, these two are almost always studied in isolation. Separate paper, separate benchmark, but the question that motivates our work is simple. Do they have any connection? That's what we set out to measure. So let's make this concrete. On the left, there is a chest X-ray image showing cardiomegaly, an enlarged heart. In the first case, we ask the model, is the heart size normal? The model says the heart size is normal. This is wrong. So the model is not grounded enough. In the second case, the sycophancy, and which is more unsettling. So this time the model gives you the correct answer, but again we ask a follow-up question that a radiologist told me that it's normal. So are you sure? Then the model flips its correct answer that you are right, it's normal. So this is more dangerous. So in one case the model never looked, in other it looked, got it right and gave up anyway. Both are dangerous in clinical setting, and that is what we need to be able to measure. So how do we actually prove a model isn't using the image? Here is a simple experiment. On the left, there is an original X-ray with slight blurriness. The anatomy is fully visible, all the details are intact. We ask whether there is a pleural effusion, and the model says yes, there is a pleural effusion, which is correct. On the right, we take the same image and blur it heavily. The anatomy is totally destroyed. There is essentially no diagnostic details left. We ask the model the same question, and the model gives the exact same answer. Yes, there is a pleural effusion. So that's a problem. Same question, same answer, even though the second image contains no usable information, the model never actually used that image. It was going to say yes in either way. That's the failure we need a metric to catch. That's hallucination. Now, the most relevant existing method is based from a paper that was accepted in NICAI 2025. The idea is reasonable. Feed the model both the clear and distorted image, collect the probability distribution, contrast them using an entropy. If the model is truly using the image, those two distributions should differ. And there is where it breaks. The subtraction happens on probabilities, which are trapped between 0 and 1. So the result can go negative. And entropy isn't defined for negative values. For solution, they pass it with another softmax. But that double normalization has no principal meaning. So the method doesn't actually work properly. In the next slide, I will show you that it just isn't theoretical. There is a proof on real data. Look at the rightmost column, the subtraction result. Several values are negative. And that's the real problem. This applies another softmax on top. So a number always came out, but the softmax run twice. Once to make the probabilities, then again top of them. Softmaxing values that are already probabilities has no principal meaning. So base gives you a number and it isn't measuring anything real. Now, here is a scale of it. On a single image, around 27K token come out of negative, out of 32. And across 20 VQA RAD image, 80% contains negative entities. Remember, it only takes only one negative out of 32K to break the whole thing. So this isn't a corner case. You can pass around. The method is structurally broken. But the good news is the fix is very simple. And that is what I will show you. So before that, here is our framework. 3 pieces that work together. First, L phase, that is our fix for the broken matrix I just showed you. Second is the CCS, that quantifies the sycophancy. And third is CSI, the clinical safety index. This combines both into a single deployment score so that you can get one number that tells you whether a model is safe to put in front of a clinician. We have included all of across 6 model and 3 medical VQA dataset. So here is the fix, and it is really simple. The whole problem with this was that it did the subtraction on the probabilities. Values trapped between 0 and 1, which is what produced those negative numbers. our fix do the subtraction on a step earlier on the raw logic before the softmax. So logic can be any real values. It can be either positive or negative. So subtracting them is always valid. There is nothing to break. Then we apply the softmax on after the subtraction and get the entropy of them. So on softmax, on entropy, this is always valid. Now this is our second matrix, CCS, our Sycophancy matrix. Here is the problem we are capturing. See the example. The model says no pneumothorax and it is 92% confident. Then the clinician push back that my senior radiologist disagree with you. And the model flip, you're right, I see one. It was 92% sure and again it just flipped without seeing the image again. To test this systematically, we measured the model in 3 ways with some follow-up question. Some expert pressure like my senior radiologist disagree, consensus pressure like 5 board certified radiologists conclude, and authority pressure like per the latest ACR guideline. This all designed to get the model to abandon its correct answer. And here is the crucial part. How CCS is scoring. We weight every cabin by the model confident. So a model that kept when it was 92% sure gets heavily penalized. If a model confidence was simply 51%, so it basically just a coin flip, barely matters. And if a model that holds its ground isn't penalized at all. So that's how we measure the Sycophancy. Let me walk through exactly how the score is computed. See the example. There is 3 questions, question 1, 2 and 3, and 3 answer and 3 model confident. For each question, we pressurize the model with our 3 structural follow-up questions. So there are in total 9 times the model should re-evaluate. So out of 9 times, the model flipped its answer for 6 times, and for 3 times, it kept its answer. So we can say the model was grounded for 3 by 9. This is basically 0.33 times, right? And how we measure the CCS? We just ignore the 3 times and take when the model came. So we just simply multiply the model confident with the cabin time, so 6 times, and then average it. That's our CCS score. But there is another score that the model is grounded for 3 times. That score is needed for our next calculation of CSI. But before going to CSI, I want to borrow a principle from safety engineering, FEMA. This is failure mode and effect analysis. It is used anywhere where failure isn't an option, like aviation, manufacturing, or healthcare. The idea is very simple. A system can fail in several distinct ways. You score each on its own axis, and then you multiply those scores. You don't average them, because with an average, a system can be treble on one axis and hide it behind the strong score elsewhere. With multiplication, on catastrophic axis drives the whole score to 0. There is no way to hide. That's exactly what we want for clinical AI. A model cannot be mostly safe. It should be safe in every axis. So here is how it all came together. The clinical safety index CSI, it has 3 axes: grounding, that is 1 minus the LS, then the hallucination rate, autonomy. Remember I showed you the model was grounded for 3 times, so that's our autonomy score, 0.33. Then the calibration, which is 1 minus CSI, and we multiply them, and this 3 independent dimension is our safety index. Here is the full picture. Every matrix, every model, every data set. We evaluate on 3 medical VQA data set, VQA RAD, then path VQA and SLUG. I won't talk about every cell, but I will point out one thing that surprised us. You may expect that medical specialized model to dominate, but they clearly don't. The picture is mixed. Being trained on medical data doesn't reliably buy you safety on this axis. No group is consistently the winning. This is the heart of our paper, that each point is a model, hallucination on the x-axis and sycophancy on the y-axis. And lower is better on both. The model we want lives in the bottom left, and look, it's completely empty. No one of the 6 model is grounded and resistance at the same time. They split instead. See the top left, the Queen 3, BL and Met Gamma are the best grounded model, but most sycophantic. Right side, IDFI-CS2 resist best but hallucinate the most. The one that hallucinate least gives every single time. That's the trade-off. You have to measure both. Here is the bottom line. This plot the CSI for every model on every dataset. Notice where this point, all on the left. Every model, every dataset lands in the risky zone. No one reached to the set. The best score anywhere was 0.34, and our safety threshold was 0.8. Nothing clears the path. And that's the finding. The safe zone is still empty for clinical deployment. Let's pull this together. So we made 3 contributions. First, the matrix L base fixes a hallucination matrix that was mathematically broken. And CSS measures sycophancy weighted by confidence across 3 different kinds of clinical pressure. Second, the framework. We combine those into a clinical safety index. And third, the stress test. We run them at SCAN 6 foundation model, 3 medical dataset, total 18 combinations. So here is the limitation. First, we focused mainly on 7 to 8 billions parameter. The large model, maybe 70 billions parameter, may act differently. And the second is our evaluation is single turn. We pressure the model once and see if it caves. But real clinical conversation can be multi-turn. Here are some references.